All right, after looking at the Desmos version of this question, let's go ahead and take a look at an algebraic solution, probably the way that the writers of the question intended it to be solved. So you might have looked at this question thinking it was pretty tough, like there's no way with my Algebra 1 background and what we've done in geometry so far, I don't have the tools necessary to solve this. However, I'm going to show you that you actually do. So I've called up the Algebra 1 TEKS, so that's what this document is here. It's actually all the high school TEKS, and Algebra 1, even if you took it in the 8th grade, is considered a high school course. And our TEKS, Texas Essential Knowledge and Skills, were adopted in 2012 for all of our math classes. Haven't changed in a while. It's 12 years. Okay, anyway, if I scroll down here to number 8 is about quadratic functions and equations, and specifically we're looking at A, so 8A. Solve quadratic equations having real solutions by factoring. We've done that quite a bit in class. Taking square roots, that works in some cases. Completing the square and applying the quadratic formula. It's these last two which provide a hint on how it is that we are supposed to solve this question. Now, I know that not a lot of classes get to this whole completing the square thing, so I'm going to take this as an opportunity to show you what it's all about. It's pretty cool, and it's actually easy enough to understand. So, completing the square means that what you're going to do is you're going to take this quadratic equation here, and you're going to turn it into a perfect square trinomial. Basically, what it's happening is this. Remember when we were saying that if you have one real solution, what happens is that the vertex of your parabola is exactly on the x-axis. So let's say, for example, this thing right here is the number, I don't know, 10. Then the equation of this parabola becomes y is equal to, in parentheses, x minus 10 and square. This is a perfect square trinomial. And if you if you expand this thing out, the way it expands is x squared minus 20x and then plus 100. You may be wondering, like, how the heck did I get this 20 so quickly? Again, it's based on the factoring pattern of a perfect square trinomial. Anyway, this thing factors as this x minus 10 quantity squared. This is a perfect square. And our job is to try to turn this kind of thing into that. And that's what's going to give us this 289. So the easiest way to kind of understand this is with these things called algebra tiles. And maybe when you were in algebra working with quadratics for the first time, you saw this happen. So instead of looking at our equation, I'm going to simplify it to some very, very, very simple cases. So here's our first one. Let's say that I have x squared plus 2x, and then I want to know what is the number that I have to add to the rest of this quadratic so that I can get a perfect square like this. Okay, and so I represent each one of these quantities with geometry, essentially. So I'm going to represent the x squared with a square. And the reason why is because this is an x by x in terms of size, which means its area is x squared. All right, so that's this first term here. And then the 2x is going to be represented by a rectangle whose area is 2x. That just simply means that when I draw my rectangle, it's going to be 2 wide, like 2 down here, and then it'll have a width of x here, okay? Now, the idea behind turning this thing into a perfect square is, well, I've got a rectangle right here. If I put these things side by side, well, then it just makes a slightly larger rectangle, right? But I want this thing into a perfect square. So what I do is this. I take the rectangle that I have that's formed by the 2x rectangle and I cut it in half. Okay, so whenever I cut this thing in half, now I have two of these that are basically a 1 and a 1, and it has a width of x here. Now what I'm going to do is I'm going to put one of them on the right side of the square, and I'm going to put the other one on the top side of the square. So let me do a little bit of erasing here. And I'm going to duplicate this guy. Right? Dupe. And like I said, I'm going to put one of them up top. Put it right there. And then I'll put the other one right here on the right-hand side. And what I've just created here, let me get rid of all these little ones. This one is a 1 and this one is a 1. And what I have to do is I have to add a little square to the corner of this, and now this turns this shape into a perfect square. Now, the area of the square that I just added here, it is a 1 by 1, so it's an area of 1. I'm getting that because the width down here is 1, which carries over to the bottom of the square, and the width on this left-hand side carries over here. It's a 1 by 1. So I basically just have to add the number 1 to this to turn this into a perfect square. And how this thing factors is by looking at the side length of this square. The side length of the square is just an x plus the 1 that's over here. It's x plus 1. And so this is going to factor as an x plus 1 squared. Okay, so there's one example. Now, let me show you just one more. Now, it gets a little bit more complicated when you have an odd number right here in the middle term, because remember what we're going to do is we have to split the thing in half so I can put one of the rectangles on both sides, right? You can still do it if it's an odd number. I'm not gonna, because I don't need to. And the reason why is because I'm just trying to show you, what the process of this completing the square is all about. So let's say that I do x squared plus 6x plus something. And I'm trying to figure out what the something is to turn this trinomial into a perfect square trinomial. So again, I'm going to represent this thing geometrically. I'm going to draw myself a square to represent the x squared, because it's an x by x. There's my x squared. And then I need a rectangle to represent the 6x. So I am going to have a length of it of x, and then its width is going to be 6. So I'll represent it like this. And just like before, I'm going to take that 6x rectangle, and I'm going to split it right down the middle. I'm going to cut that thing right in half. That didn't look like half. Okay, this is better. And now I'm going to put one of those rectangles, one of these two rectangles I just formed, I'll put it on the left-hand side of the square, and then I'll put the other one up here on the top. So I'll do the exact same thing that I did before. And duplicate this thing perfectly. And duplicate and put one of these guys up top, right there. And I'll scooch this one over a little bit closer. It's nice and cozy. Okay, so the width of this is not 6 anymore. I just split it in half, so that width is now 3. So I'll put a little 3 here, which means this one is a 3. And to complete the square, I have to add myself a little square to the corner of this thing. And the number that I just added is essentially the area of that little red square. Well, I can see that it is a 3 by 3, which means that I just added an area of 9 to this. And so 9 is what completes that trinomial into a perfect square. And in order to factor this thing, what I do is I figure out what is the length of my square, and the length of my square is an x plus 3. So this factors as x plus 3, and then squared. So now, you don't want to have to draw this picture every single time you do this, so let's just kind of make some connections here. Let me scooch this picture down just a little bit. So remember what we did for this over here on this first one is that we took the 2x rectangle and we split it in half. That's what we're going to do. We're going to take our 2, not the x part, just the 2, and we're going to take half of that. So that's a 1. And now, in order to get the area of this little square, essentially it was that number 1 squared. So I'm going to square the 1, and whatever number I get is the number that I have to add to complete the square. Let's do that again right over here on this one. Scooch this thing down. Originally, I had a 6x rectangle, and in order to get each of these 2 rectangles that I split it into here, I took half of this. So I'm going to take half of the 6, not the 6x, but just the 6. So take half of that, and I get a 3. And now, in order to get the little square that I had to add to this, I essentially had to square that 3. So I'm going to square that number. And 9 is the number that's going to complete the square. So now let's go back to our question, and we have enough background to be able to answer this question, I believe, how it was intended to be answered. And you can answer it, like if you understand this process, this question is rather simple, and it takes you just seconds to finish it. And it'll look like this. I would have my x squared minus 34 And then I have to complete my square by adding something. Whoops, 34x. So just like before, I'll take half of this guy, and I'm going to bring that negative sign along with it. So half of negative 34 is negative 17. And now I've got to square that number. And when I square it, I get my 289, which is the same number that we found with Desmos. And again, like if I understand the process of completing the square and I make a connection between that's what I have to do, because completing the square puts the parabola exactly on the x-axis on its vertex with one solution. And as soon as c is bigger than that number, then my parabola is now off the x-axis and I have no real solutions. Right? Then you can see that the solution takes, it takes seconds. That's it. That's the whole entire solution. Now, you may not have learned completing the square when you were in Algebra 1. Here's another method, and the other method has to do with the quadratic formula. So let me pull the quadratic formula here off the top of my head. So the quadratic formula, you know it goes like this. To pop goes the weasel. X is equal to negative b plus or minus the square root of b squared minus 4ac all over 2a. So this whole idea of having, say, two solutions for a quadratic happens when the square root here is a positive number. So whenever you take the square root of it, you're going to add and subtract that from negative b. That's what gives you your two solutions. However, when your b squared minus 4ac is a 0, then you're adding and subtracting nothing, and that's when you have just a single solution. And that's what's happening right here when our parabola is exactly on the x-axis at its vertex, okay? However, you may remember that when this thing inside of the square root, which we call the discriminant, when that discriminant is less than 0, you're taking the square root of a negative number. Square root of a negative number is not a real number, and so that's what's giving us our no real solutions. So you might remember that part from Algebra 1. So when the discriminant is specifically b squared minus 4ac, when that quantity is less than 0, you have no real solutions. So now let's just apply this to the equation that we had. And our equation was x squared minus 34x and then plus c is equal to 0. So my a value here is 1. It's this understood 1 here. My b value is negative 34 right there. And my c value is equal to, well, it's c because I don't have a number for that. Now let's just plug all of this into our little discriminant here. So I'm going to have, what an ugly arrow. You don't get to stay. That's better. All right, my b squared, I got a negative 34, which I'm going to square, minus 4 times my a value of 1 times my c value has got to be less than 0. Okay, so now I'm solving this thing for c. And it's an equation, it's an inequality, an inequality. You're going to solve it just like you would solve any equation, but the only difference, there's two major differences. You have infinitely many solutions when you're done instead of just a single one. And the second difference is the fact that if you have to multiply or divide by a negative number, it's going to flip this inequality sign over. Anyway, so if I'm going to solve this thing by hand, I got to square this negative 34 here. So negative 34 squared. You know what? I'm not even going to worry about what negative 34 squared is. I know that it is a positive number, so you can kind of ignore the little negative sign, right? Because when you square this thing, it's going to be a positive number. Okay, so what I'm going to do is I'm just going to take this quantity, I'm just going to bring it over to the other side. So I have a negative 4 times 1 is just negative 4 times c is less than. And whenever I take this to the other side, again, I'm ignoring the negative because I'm going to square that number, but I'm subtracting it to the other side. So it's a negative 34 squared. Now this negative right here is no longer in the parentheses because I subtracted it over. Right? So really it's like this, right? Okay, so now I'm going to divide by negative 4. So when I divide both sides by negative 4, divide by negative 4, chink, chink, I have c is, what's going to happen to this inequality sign? That inequality sign has to flip around because I divided by negatives. And then our negatives over here are also going to cancel because a negative divided by a negative is a positive. So the only thing that I'd have to put into my calculator here is basically a 34 squared and then divide that thing by 4. So I'll just pull up my calculator just real quick and I'll put that in. And I wonder what number it's going to give me. I haven't a clue. So here, let's pull up our calculator, just go down to our next line, and I have a 34 that I'm squaring, and then I'll divide that thing, divide it by 4, and oh, would you look at that, it's 289. So if I write that like so, I have C is greater than 289, and now remember, the way that the question was formatted is that you're looking for a value of n such that C was greater than n. And what we just got is essentially this thing. It's in red here. When we solved it down here, it's in blue, but it's the same thing, right? This value is our n value. So this is our n. And C is bigger than, I don't mean to make that divided by n. That looks, no. Here you go. So this is our n value. N. And C greater than 289 makes it so that the discriminant is negative. If the discriminant is negative, you're taking the square root of a negative number, which means you have no real solutions. So there you have two different algebraic solutions of our quadratic equation for week 6.